Okay, today we're going to talk about this is unit 15F, and this is kind of cool. So it's operations in polar form. And so we get these really cool identities. This is my favorite unit because it's a great unit. So let's start off. Remember, so the idea is when you multiply when you multiply complex numbers, it's like multiplying their modulus and adding their arguments. Let's just take a look at that. So we're going to start with the first number, z1. Let's call it a plus bi, and let's call z2 c plus di. Okay. Now we're gonna turn this into a complex number. We're gonna identify the modulus. So let's let the modulus be r, and let's let the arguments r1, and let the argument be theta 1. So this is r1 cis theta 1. Okay. Now, and the same thing with r2. We have the modulus, we're going to call this R2, and the argument is theta 2. So we have R2 cis theta 2. Now, we know what this is, and this is R1, cosine theta 1 plus I sine theta 1. Let me see if you can see me perfect. And the second one, we have R2 cosine theta 2 plus I sine theta 2. Once again, this is just going to be a derivation. You're not going to be asked to do that, but this is really helpful. This is really, really helpful. So what we're going to do is we're going to multiply these two numbers together, z1 times z2. Now, you might have done this last year and you have the notes or not. So let's multiply those two things together. Well, we have r1 times r2 times cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2. Obviously, we'll use the FOIL method, keeping the r1 out here, r2. I'm going to bring the reals together. So we have cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. That's the real part. And then the imaginary part, what's the imaginary part here? The imaginary part is we have sine theta 1 cosine theta 2 plus sine theta 2 cosine theta 1. Now, what's going on here? These might be familiar to you. You might say, oh, let me go to the formula booklet. Well, it turns out that R1, R2, it turns out that this actually is the cosine of theta 1 plus theta 2. And that expression over there from your formula booklet ends up being sine theta 1 plus theta 2. And this is the proof of what's going on. When you multiply two complex numbers, it's like multiplying their modulus and adding their arguments. That's kind of cool. I think that's really cool. So once again, exactly. I'll say it again. And you have to know this. When you multiply two complex numbers, let me rewrite this. So it's R1, R2, cis theta 1 plus theta 2. Yeah, R1 cis theta 1 times R2 cis theta 2. And this is really helpful. If you think about it, this is how you can create your identities. Anyway, So this is the first thing you need to know. The other identity is when you divide. When you divide, you recall that you still divide the modulus, but in this case you subtract. You subtract the arguments. So once again, you can derive that on your own. It might be a great exercise to derive it on your own. So let's just look at some examples. So for example, good example, you can see that, so for example, I taught you, I want you to know that I is, 1/6 90. Well, what's I times I? You'd say, okay, well, I times I is -1. But if we're multiplying two complex numbers, it's like adding their arguments. Well, I cis 90 times I cis 90 is like 1 times 1 cis 90 plus 90, which is 1 cis 180. And we know, because I asked you to practice this, you can see that, right? Yeah, we know that this is 180, or -1. I times I is -1. It's very straightforward. How about we try a little more advanced, or -1 times -1. Well, we know -1 is at 180. 180 plus 180 is 360. Let's write that down. Let's just move the camera over. So once again, -1 times -1, well, this is I cis 180 times I cis 180, which we know is 1 cis 360. I visually know where that is. I know that's right here. That's 1. A negative times a negative is positive because 180 plus 180 takes us back to 360. This is why this is the best lesson in the world. It makes all these weird lessons about negatives. It just makes it easy. As I said before, turn all your numbers into a geometry with a modulus and an argument, and all these lessons from it just makes it much easier. So and the other thing you need to remember is like these 30, 60, 30, 45, 60. So for example, if I say, 1 plus I times 1 plus I, because you just visually see it, you're like, okay, wait a minute, this argument is 45. You know it's right there. And from Pythagoras' theorem, once again, so this is 1 plus I. You know this, the modulus is radical 2. So if I say 1 plus I times 1 plus I, in your head you go, okay, Mr. Rather, radical 2 cis 45 times radical 2 cis 45, 2 cis 90, 2I. That's the idea. Does that work out? Well, let's just check it. Let's just check this out. Let's see. I times 1, 1. 1 times I. 1 times I. I times I, -1. 2I. Nice. Question. Where does the division show up? Well, obviously you can imagine the exercise I'm going to ask you. But the idea is, for division, just turn the numbers into complex numbers, get the modulus and the arguments, and then you divide the moduli, and you subtract the arguments. And so you can see from the book. Let's use an example. How about -3 plus I divided by how about a negative radical 3I divided by, how about 1 plus radical 3I. So you're looking at these numbers and you're saying, what are these numbers? Well, you recognize it from your from your trigonometry. These are part 1 questions. So let's take a look at these. Let's just figure out where these are. Once again, maybe you want a diagram. So let's look at Z1. So Z1 is, radical 3i. It's kind of right there. Not really sure where it is. Radical 3 and 1. The angle here is opposite, and this is 2, right? Because you know from your geometry class. So the question is, what is this rotation here? So you say, you know what, if this is the angle opposite over hypotenuse, okay, so the reference angle is 30. So therefore, theta, theta 1, is 150 degrees. Okay, let's take a look at the number in my denominator. Z2, I'm going to draw it clearly. It's in the first quadrant, 1 radical 3. So it's 1 radical 3. Once again, the modulus is also 2, but it's not the same angle because the sine of radical 3 over 2, that was 60. So once again, if this is theta 2, we know that the sine of theta equals radical 3 over 2. You know that theta is 60. Okay, well, now we're ready to do some work here. So we're going to rewrite these as 2 cis 150 over 2 cis 60. Well, the rules simply say 2 divided by 2 is 1. 150 minus 60 is 90. The answer is I. Now, you can do that by hand. Put it in your Actually, no, that would be an exercise. Use your graphing calculator to do this operation, and you should get the answer of I. Nice. Now, what else is division used for? What else is division used? Well, it's great for reciprocals. Let's think about this. What is 1 divided by cis 60? So, and before you'd have to go through the whole thing. You'd have to expand this out, and then, multiply. In the olden days, you'd be like, okay, cosine 60 plus I sine 60, which is equal to 1 over, 1/2 plus I radical 3 over 2. And then you'd have to multiply it by the conjugate. No, you don't have to do that anymore. 1 over cis 60, now rewrite the 1 as 1 cis 0 over 1 cis 60. This is now 1 cis negative 60. And this explains why 1 over a conjugate, 1 over a number is equal to its conjugate. That's cool, I like that. Once again, so when you see reciprocals like this, 1 over a complex number, rewrite the numerator as a complex number with a modulus and an argument, and then just go through the operations. Let's move on. Nice. Now, here's the great thing about complex numbers. I mean, we've done the operations and stuff, but let me move back over here. Just remember, this is awesome. Just remember that when you multiply by a complex number, you're merely rotating it by its arguments. That's it. Once again, multiplying a complex number by cis theta rotates the complex number by theta around the origin. So if I take any complex number and I multiply it by cis 90, you've just rotated 90 degrees. That's it. And so, I mean, that's it. It's really awesome if you think about it. I mean, pick anything. Yeah, pick an like 7. 7 is what? It says 0, right? If I multiply that by I, it's now, multiplied it by 90. You've now rotated by 90 degrees. If you multiply if you take a complex number, and you multiply it by, 1 plus I, well, if this is 45, you just rotated it 45 degrees. That's it. And so you see this problem in the book. It's an amazing problem. You might see it you might see this on the IB exam. The question in the book is, sorry about that. Simply put, you're given a triangle. If you look at the problem in the book, it's kind of cool. You're given a triangle. And they tell you the center, it's centered around 0, 0. It's centered around 0, 0. And one of the points of the equilateral triangle is 1, 2. And they say, what is the other point? What is the other point? And if in the real plane, this is really difficult. But in complex numbers, it's really easy. Once again, we have an equilateral triangle. And the question is, what is the coordinates of the third vertex? So in complex numbers, you're like, this is easy. All I have to do is rotate this 60 degrees, or pi over 3. So step one, turn 1, 2 into a complex number. So what is 1, 2 as a complex number? You say, okay, well, it's 1 plus 2i. Next, multiply that by 660. That's it. What is 660? Well, you know that from before. We know from before it's 1/2 plus I radical 3 over 2. And that's it. You just multiply. So 1 plus 2i times 1/2 plus radical 3 over I. Multiply these together. 1 times 1/2 is 1/2. Let's do the reals together. So 2i times I, well, the I times I is negative. And then 2 times radical 3 over 2 is radical 3. And now let's do the imaginary parts. Let's see, we have 1 plus radical 3 over 2. And then 2 plus 1/2 plus 1, right? And so, once again, it may be a little difficult. It's easy in complex numbers. So this coordinate is, what is it? It's 1/2 minus radical 3, comma, radical 3 over 2 plus 1. Now, if you thought about it, we never asked you these questions in geometry. We never said, here's 3 points, here's 2 points of an equilateral triangle, find the third point, because it's really difficult. But now in complex numbers, all this is easy. We see the complex number is centered at 0. The triangle is centered at 0, 0. Rotating a point 60 degrees, it just means multiplying it by 660. That's it. It's kind of awesome. Couple of other things. So the unit it seems like a small unit, but no, it's really powerful. It's a really powerful subunit. Let's continue with this. Now, let's raise to the power and see if we can kind of come up with a formula we're going to be needing. So the question is, what is z to the n? The question is, what is z to the n, right? So we know that this is, z times z times z n times, correct? Well, we know that this is, the modulus to the nth power, and we know that it's like it's n times the arguments, right? Because we're multiplying, right? Because we're adding n arguments. It's like n theta, right? Now, this is kind of interesting. If we rewrite z as r cosine cis theta, then r to the n is now r to the n cis n theta, and that's where de Moivre's formula comes up. Once again, based on these rules from today, that when you multiply complex numbers, you multiply their modulus and add their arguments. If I'm raising something to the n power, I'm multiplying the modulus to itself n times, and I'm adding the argument n times, which results in n theta. We're going to see this how important this is in the next lesson. Now, the last thing I want to talk about is this question where in the book, and I want you really to practice this homework because it will really help you with the last unit. Once you get this down, once you get 15F down perfectly, you're in great shape. So the book gives you this problem. It's number 3 at the end. It's number 3 at the end, and they tell you that z is cosine pi over 6 plus I sine pi over 6, which we know as cis pi over 6, or for someone like, you really shouldn't do this, and make sure that if they ask in radians, they want to know radians, but for my sanity, I write cis 30. You should do it's like speaking 2 languages, but make sure you know what language you're in. Are you in the world of degrees, or are you in the world of radians? You know that you can go back and forth. So they say write z squared, z cubed, and z to the 4th in cis form. Well, we know that we're multiplying. If with z squared, we're taking cis 30 and multiplying by cis 30 again. Well, what's that? Well, that's cis 60. To the 3rd power, they're telling us to multiply 2 rotations of 30. They're getting this idea of when you multiply it by a complex number, you're rotating it by that argument. So we're asked to start at cis 30 and rotate it twice, z to the 3rd, cis 90. And obviously, you can say, hey, Mr. Adler, it's 4 times 30, so it's cis 120. Please, I can't stress this enough. When you multiply by a complex number, you're rotating it by its arguments. It's a really cool concept. It's so powerful. And then they ask you to put it on the Argand diagram. And once again, this is it's preparation for the end of the unit. This idea that these will be roots, but they're just numbers and they're going in circles. Like this is cis 30, and this is cis 60, and this is cis 90. And this is cis 120. And you say, it's going around in a circle. It's going around in a circle. They're all on the circle, so they have the same modulus. And they're all equidistant. And you're kind of building up this idea of, eventually it's going to come back to the first root. So once again, just practice these problems in 15F. So just to summarize, when you multiply by a complex number, you're multiplying the modulus and adding the arguments. When you divide 2 complex numbers, you're dividing their modulus and you're subtracting their arguments. And when you raise a complex number to a power, you're raising the modulus to the power, but you're multiplying the arguments by that power. Good. Practice 15F. And I'll put some other problems up because this is so important.